All right, folks. I have no idea who's here. Let's take a look. I've got 3 people here already. Fantastic. I had to run to the school real quick to grab another beaker, but I think we're okay. So, can you, if you are here, can you just check in? Who have I got? Who have I got here? Yep. Connor May. Hi, Connor. How are you? You don't need to reply to that. I'm just asking. And I got Kaylee. Yay. Kaylee's here. And who else have we got? Kate Patterson. Hello, Kate Patterson. And that's the 3 I've got. Thanks, folks, for being here. Fantastic. All right. So let's start with this question. And Connor, Kaylee, and Kate, who is. Actually, here's let's start with this question. What causes wind? What causes wind? You can write that answer there. That's the question we're going to be examining today. Another way of heat transfer. Okay. I think it might be a problem at your end. I don't think it's a problem at my end, Kaylee. Sorry. I'm assuming that Kate and Connor can hear me. Can we just have a sound check on that? Kaylee and Connor, sound check. Oh, Jenna's here as well. Hi, Jenna. Connor, can you hear me? Connor. Oh, fantastic. There we go. Temperature. Thank you. Excellent. So, hi, Ava. What causes wind? What causes wind? I've got Connor saying temperature, which is an excellent answer if we were studying about a heat unit. Great answer. A pretty safe bet. Any other ones? What's another reason why we could have heat? Weather or wind. Thank you. Weather. Okay. And this actually causes weather as well, which is kind of cool to think about. If you have, okay, if you want to take notes, because one of the questions on the sheet is, I'm going to show 4 different ways that we see convection around us, and you can pick one of those to draw or write about. Okay, so if you're going to draw, although it's going to be digitally, you can take a picture of it. You're going to need a blue and a red marker, okay, or something. Okay, if you want to do that, or you can just learn it and do it from there. 6 people in. All right, so this is convection. Okay, so we talked about heat transfer last time in conduction. Okay, so conduction works like this. This molecule starts to get hot. Okay, and it bumps into, the sheets. Ava, the sheets in the same place you found, in Google Classroom under conduction. Okay, so you may want to grab that. That's a really good idea, Ava. You may want to grab that while we're going to here. Okay, I can't show you I can't display my screen, so I can't show you it. Okay, so conduction, that's what we said last time. All right, conduction is one molecule getting hot. Okay, so it works well in solids. That was one of the answers that I was looking for. It works well in solids. Hi, Jacob. Okay, it works well in solids. So this solid molecule starts to move faster because it starts to get hot. Okay, I'll have to put it up there then, Kate. I'll have to look. Let me just see. I'll put a pause on the video for a minute and try to finish discussion later on. Classroom. I'm just going to try to get to it. Looking. I don't want this to start heating up yet. Okay, science grade 8. Convection, another way heat travels. Convection, another way heat travels. Ah, hold on. Oh, you're right. For Pete's sake. Okay, just give me a minute. Okay, thank you for telling me that. Edit. Give me a small moment here. Add. I'll drop it in real quick. There it is. Sorry, folks, I didn't add it in there. You'll notice that there's also a quiz. I mean, you are welcome to do the quiz right afterwards. Oh, I can edit, but I can't share with each student. All right. Because of the way that this is working, I won't be able to give you each a copy for some reason. So you're going to have to make a copy of it. Okay. I'll write that in the instructions. There you go. So the sheet, it should be up there momentarily. Okay. All right. Yeah, I just put it in there. You may need to refresh that page. Okay. So I'll give you a little bit of time to find that, and then we'll go from there. Okay. I'll blow this out. All right. Kaylee, can you hear me now? Weird. I don't know what happened to it. Let me hit convection quiz. Oh, it's just a Google form. Yeah. Oh, yeah. Okay. I don't know. I just put it in there. So, okay. Thanks, Jenna. That means it's there. That means we can get going. All right. So, conduction. Okay. Starting again. Conduction works well in solids. All right. Not well in gases and liquids. In a solid, God created heat to be transferred because this molecule starts to move faster. Okay. It gets heated up. Okay. May as well heat it up. So this molecule gets heated up. Okay, there's a flame here. Gets heated up, starts to move faster, bumps into this one and starts to make this one move faster. Okay, this one starts to move faster, then this one starts to move faster, and it moves down the line. Okay, that is conduction. All right, so molecule transfer, bump, all the way down. Convection is different. So God saw, okay, in the beginning, he said, hey, I can make heat transfer through solids, but you know what? We need heat to be transferred through the air, gas, and through the seas, liquids. So God had to come up with another way to make heat travel. All right. If this type of form of heat transfer didn't be created, okay, then places on Earth that the sun hit that got really hot would stay really hot, and the places that were cold, like the North Pole, would stay really cold because the heat wouldn't be able to get from one place to another, or especially us. Okay, hi Riley. So God created convection. Now, convection, like I said at the beginning of this unit, if you know the kinetic molecular theory, right? Heat makes things move faster, makes molecules move faster, then this feeds into that as well. I'm going to show you convection, sorry. I'm going to show you convection, okay, in this beaker. So let me just adjust this. And then we're going to talk about how we see it all around us. All right. And one of the big ways we see it is wind, but there are some really cool ways that we can see it around us. So this substance is potassium permanganate. Okay. And I am going to put it in the side over here. Okay. And we're going to watch to see what happens. Okay. So it's a solid, but it's a purple solid. Okay. We're just going to wait while it gets heated up. I put this water in the freezer, hoping that it might even be able to show it better. Let me get a white piece of paper or this right behind it. Okay. Okay, perfect. You see already that it's happening. Okay. You see the purple, the potassium magnate, the color going up. Okay, this is a liquid going up, going across, and going back down. Okay, going up, going across, and going back down. I have to add a Eureka video into the classroom as well. Okay, that will help. Goes up, goes across, and goes back down. This very simple thing is convection. Okay, it's usually called a convection current. It goes up, it goes across, and it goes back down. Now, why does that happen? Okay, and this experiment only works for a very short time because you can see that it starts to get really, really messy. All right, but you can still see the cycle. Okay, convection current. It goes up, goes across, and comes back down. And you get this loop continuing to happen, continuing to happen, continuing to happen. Okay, so we know that when molecules heat up, they move, type it in. When molecules heat up, they move. So you got it in there. Hey, Kaylee and Riley, thank you. Okay, good. Thank you. They move faster. Okay, now we learned from our effective heat that when they start to move faster, it needs more. Get it in. Kaylee, you're going to have to watch the video and you'll learn to go from there. Room. Okay, good. Thank you. Okay, thank you, Kate. So it needs more room. Now, because it needs more room, what's the word I'm looking for? Effective heat. Because it needs more room, there's more space between the molecules, so the whole thing. Hey, there we go. Okay, thank you. The whole thing expands. Okay, so the whole thing expands. Now, that's going to get important because that's what's happening here. Okay, I won't be able to see it anymore, but the molecules down here, okay, they started to move faster. They spread farther apart and it expanded. Now, that may not seem like a big deal, but anytime, okay, so this is really important to remember. Anytime that, let's do this. Here are my hot molecules. Okay, hot liquid molecules. Okay, can you see that? Yep. Okay, and here are my cold liquid molecules. Okay, this bundle of hot liquid molecules are farther apart. Okay, that when they're farther apart, it makes them, and here's the next connection, it makes them less dense. All right, so this becomes less dense than the liquid molecules around them. Liquid molecules around them are pretty close together. Okay, they're moving like this, they're moving, okay, they're pretty close together. These molecules, the hot molecules, are a little farther apart. So they're less dense. As soon as something that is less dense, okay, as soon as something becomes less dense, it rises. Okay, it rises. That's what's happening here. These molecules become less dense. These molecules become less dense and they rise. And they bring the potassium permanganate with them. They rise. That is, in essence, convection. Okay, so Kaylee, if you're looking for a quick definition, and you know this because you've seen it all before, okay, here's a really simple one. Heat rises. Heat rises because it's less dense. Okay, now we know this. We've seen this all around us before. Okay, we know that phrase, heat rises. So the molecules spread out. Okay, so here's my molecules. Okay, here's my molecules at the beginning. These molecules get heated up, they spread out, and because they're spread out, they start to rise. That is convection. That is convection. Okay, heat rising. Now, why do we end up with a cycle? Well, as they get away from the heat source, so my finger's gonna be on molecules again. Okay, maybe I'll do it over here. Okay, so here's my cold molecules. Okay, these molecules get hot, so they start to rise. All right. Ooh, I wonder if I could do that. Hold on, give me a minute. Sorry, teaching this online is like way different. Okay, so I'm gonna have to use my fingers to help. There. Okay, so if you see, right, these are my cold molecules. Okay, they're pretty close together. These molecules become hot, so they start to spread apart. You can see that I made them red. Okay, they start to spread apart. As soon as they start to spread apart, they rise. Okay, that is in essence convection. Now, as these rise, okay, as they get cooler, as they rise, they get away from the heat source, they start to cool. As they cool, okay, they become more dense again. Okay, and so they sink again. So I'll do it this way. Normally what I do is I have it in the classroom, all right, and then we walk around, right? We pretend that we are molecules and we rise, we get farther apart, we rise, we get colder, we sink, and then we come back down again. But here I just got to do it like this. Okay, so cold molecules get hot, they rise, they become cool again because they're away from the heat source. Okay, and then they sink again because they're more dense. As they come around again, okay, they come around to the heat source again. All right, so if I would actually put a heat source here, as they come close to the heat source again, okay, they become hotter again. They go up, okay, they become cool, okay, because they become cool, they become more dense, and they come back or down again. And that's where our cycle happens. Okay, that's our convection current. That's our convection current. All right, that is in essence what this lesson is about. All right, now, and again, I'm going to put a Eureka video in there that I didn't put in earlier either. Now, where we see this is amazing. So I opened up this session with just the idea of what causes wind. Well, let's take a look at this. Now that we know this, okay, and I'm going to finish it off real quick, becomes less dense, okay, heat rises. Now, heat rises, and then if I were to go backwards, okay, it cools as it gets away from the heat source. As it cools, okay, the molecules move slower. As the molecules move slower, it needs less room. As it needs less room, okay, it sinks. And then it gets to the heat source again. Okay, and then we have this cycle going around and around and around and around. That's what's happening here. Okay, now think about where you see these circles in everyday life. I'm going to give you 4 examples. At the bottom of the sheet, it says, hey, tell me about your favorite one. You could draw a picture. Like I said, if you're going to draw a picture, you need a red and blue. Okay, or you can just describe it. Okay, so I'll start with a very simple question. Okay, what causes wind? Well, wind happens because one part of the earth gets warmer than the other parts around it. Okay, so I usually go with example. Actually, it comes from my grade 11 geography teacher. Okay, if you stand on a parking lot, a parking lot absorbs heat. You'll learn about this at the end of this week. A parking lot absorbs heat like crazy. Okay, now, so we've got this pocket of air above a parking lot. This pocket of air, I'm just going to use arrows now instead of drawing molecules. becomes hot. The molecules move faster, needs more room, the space between the molecules expands, it becomes less dense, and it rises. Okay, so all over this parking lot, all of a sudden you've got this pocket of air going, okay, going straight up. Now, if you're standing here and all this air left because it became less dense, you would have a problem, right? So there's no air around you, you would die, okay? But God said, hey, that's stupid. I don't want people to die because there's no air around. So I'm going to create wind. When this pocket of air goes up, air rushes in to take that place. Okay? This air is coming in to take the place of that air. Okay? Now, if you're standing here and you feel this rush of air going past you, what do we call that? Type it in. Air is moving past you. You're standing in one place, air is moving past you. What do we say? Oh, it's awfully blank out. Yeah, okay? It's windy out. That's what causes the wind. Okay? This pocket of air goes up. Okay? This pocket of air goes up. This comes in the side. Okay? Now to finish off the cycle, then this becomes cooler and comes back down again. So we have this cycle. Okay? But this right here, what we feel here, that's the wind. Okay? That's the wind. Okay? Not air. Oh, thank you. Yeah. Okay? Airy. No, it's not airy. We feel windy. Okay? So that feels wind. Okay? So we feel the wind go past us. Now we know this. Okay? So here's a really practical example. Okay? Hopefully we feel this summer. All right? Here is a beach. So this person is now standing on a beach. Okay? He's not dead anymore because wind came in and saved him. Okay? This person is standing on a beach. Here's the water. Now, the water, okay, in the heat of the day, okay, the water is going to be cooler than the land. The land heats up. That's why when you walk on sand on the land, okay, on the beach, it's really hot on your feet. This land is getting really hot. Well, we know that the pocket of air above it, okay, is going to rise. Okay, and we're going to get wind. It's called an onshore breeze. The wind's going to come this way. All right. Now, how many of you have ever flown a kite at the beach? Okay. Type in if you've flown a kite at the beach before. Okay. If you've flown a kite at the beach, you're going to go this way because that's where the wind's going. Okay. Anybody flown a kite at the beach? Hey, there we go. Okay. Now, this is your onshore breeze. This air has left. The land is really hot. It heats up the air above it. That air, again, I'm going to go through it because the more times I go through it, the more it'll sink in. The air molecules move faster. They need more room. Molecules spread farther apart. It expands. Because it expands, it becomes less dense. Because it becomes less dense, it rises. This air leaves. This air rushes to come in. That's why when you fly a kite this way. That's why it's windy on the beach, because you have all of this. Now, what's cool is that sometimes at night, the opposite happens. Okay, so this was called an onshore breeze. At night, the water ends up the land cools off really quickly, so the water ends up being warmer. So the air above the water ends up being hotter, and it rises. So at night, you have a breeze going in the opposite direction because this is going this way. Okay? So this goes this way because this air rises up. And then sometimes you experience at night, sometimes not. Okay? You have an offshore breeze. It goes this way. Okay? So you fly your kite in the opposite direction. I don't know if I've ever experienced that, but theoretically that should happen. Okay? So that's a very, very simple thing. So for that last question, you can talk about, I'll put them up here. You can talk about wind in general. You can talk about onshore offshore breezes. By the way, in each of these answers, I'm going to be looking for, okay, air heats up, molecules move faster, they spread out, becomes less dense, rises. Okay, that sequence of events. So those are two examples you can put down. All right. Now, wind also happens, you may remember this from geography, on a global level. So there's two ways that we're going to, actually three ways, but we're going to be looking at this on the Earth. Here's one. Okay. Where is it really hot on the Earth? Write that down. Where is it really hot on the Earth? Perfect. Awesome. By the equator. Okay, very good. So by the equator, okay, you have this same thing happening, but on a global level. Okay, so this pocket of air becomes really hot. Okay, and of course, God designed this because He didn't want this place to be really hot and this place to be really cold. God said, hey, I want the air to spread around, I want the heat to spread around. So God created convection, which works really well in solids and liquids. But you'll also find by watching that Eureka video that those are called fluids, okay, because they flow. All right, so this goes up on a global level. So we have this huge pocket of air going up. Okay. That huge pocket of air goes up. This takes its place. Now, what's kind of cool is that when this cools off, okay, the molecules move slower, they need less room, they contract. Because they contract, it becomes more dense and then it sinks. So it sinks over here. What's really cool about this line, and of course the same thing happens on this side, okay, we've got a double convection current here, okay. What's really cool about this line and this line is that's where our deserts are, because you've got this really, Jacob, because we've got these really, really cold air dropping right on these spots. And this is where you'll find, down here, you'll find the Sahara. And over here, you'll find the Atacama, for example, deserts. Your deserts are here and here. What's also kind of cool about this is that if I take the Earth and put a spin on it, which is what's happening, so the Earth is spinning, suddenly I've got this going on, okay? Now, this may not look like much, okay? So I've got the wind going in this direction. But this is the reason why Columbus discovered Haiti down here, okay? Because the wind was pushing him. Europe's over here. The wind was pushing him in this direction. Why is the wind there? Well, because this is happening. There's a convection current, okay? This is also why it takes 2 hours longer to come back from BC than to go to BC, okay? When you're flying to BC, you're flying with the wind. There's something called a jet stream up here, okay? You're flying with the wind. When you're flying back from BC, it goes longer, okay? You're fighting against the wind, so it's actually longer going back from BC than going to BC, okay? Because we have this wind being pushed around. Now, so you can mention that, okay? You can talk about global winds, all right? One more example that takes place on the Earth, okay? I'm going to keep that there, okay? But now picture it happening in the water, okay? So we know that we have oceans, okay? I'm going to need this later on anyway. I'm going to draw Africa and South America, okay? That's pretty good. North America's over here, okay? Europe's over here, okay? We've got this huge Atlantic Ocean. Now, the Pacific is even bigger, okay? The Pacific's over here. Now, this, okay, these oceans, the water here becomes hot, okay? And because it becomes hot, the water becomes less dense. Because it becomes less dense, it rises, okay? And then other water rushes in to take its place. So you got to picture this on an oceanic level. So the cold water rushes this way to take place of the hot water that's moving away. Okay, now you've got, I'm going to do it over here too. Okay, you've got continents in the way that's causing all kinds of motions around there. Okay, does anybody know what those lines are called? Okay, what are those lines called in the ocean where water is moving, taking heat from hot areas and moving them to cold areas? Okay, what are those lines called? It's the same reason why Columbus went from here to here. Okay, there was a ocean current. Thank you, Connor. Yep, an ocean current. Okay, an ocean current coming from here to here. These form your ocean currents. So that's another way we see convection all around us. Remember, one of the goals when I teach science is to have you see science everywhere. Okay, so now when you're standing on a beach and it's windy, you go, oh, science. Okay, well, hopefully you'll know that wind. Okay, but that's why it happens. Okay, why would we see currents? Well, that's why it happens. Okay, now the last one is really kind of cool. Okay. So I'm going to go, oops, I erased it. Sorry, I got to put it back in again. Here's our world again. Okay, but this time we're going to take a different look at it. Here's Africa. Okay, you can picture that. Here's South America. What do you notice about Africa and South America? And if you had an atlas in front of you, normally I pull down a map, I pull up a map to show you. It's really, really awesome, but this is the most I can do right now. Okay, what do you notice about Africa and South America? South America and Africa. What do you notice about them? Usually it takes a while in class too, right? If I'm talking about in class. Okay, thank you. Yep, they're definitely different places. Okay, and Connor's got it. Okay, they look like they fit together. Okay, they look like they fit together. This part, if you're a puzzle person, okay, would fit nicely into there. Okay, that's exactly what happened. Africa and South America used to be joined. Okay, actually, I go like this. They used to be joined like this, but they got farther and farther apart. Okay, the reason why? Science. Well, actually, convection currents. So we're going to leave this, keep that image in your head. Okay, and now we're going to take a look at the inside of the Earth. Okay, yes, other continents do the same thing. Okay, so Jacob mentioned Australia. Yes, you see this all over the place. Continents fit together. These two I like because they're really obvious examples, and you can see something really cool in between them as well. Okay, so keep this image in mind. Okay, because unfortunately I'm going to have to erase it because my whiteboard isn't that big. Okay, so now let's take a look. Now we're looking on the inside of the Earth. Okay, so looking at the inside, I cut the Earth in half. Okay, here is South America, and here is Africa, and here's the Atlantic Ocean. Okay, so can you picture that in your head? Okay, here's the Atlantic Ocean. In the center of our Earth is the Earth's core. Okay, the Earth's core is really, really hot. So, and all around, okay, this is liquid. Okay, it's called the mantle. All right, so this is your core. Okay, then you have the mantle. Okay, if you pictured a volcano, okay, mantle inside the Earth, magma outside the Earth. Okay, but it's magma, it's liquid rock. Okay, so we've got this happening inside the Earth. This is really hot. Okay, so we're going to start to see convection currents inside the Earth. This starts to rise. Okay, this pocket of liquid rock, molecules start to move faster. Because they start to move faster, they spread apart. they need more room. Because they need more room, it becomes less dense. Because it becomes less dense, it rises. Okay, it rises. So it's starting to rise. All right. Now, when it gets to the surface of the Earth, it starts to cool off. This part goes this way. This part goes this way. Okay. Then it becomes less dense. Okay, cools off, becomes less dense. You have this current. So you have this force inside the Earth pushing these continents apart. Okay, so we've got this continent being pushed this way, this continent being pushed this way. Okay, now what would you expect in the middle of the Atlantic then? If we've got two plates, okay, like this, if we've got two plates being pushed apart, okay, by the convection currents that are happening like this, two plates that are being pushed apart, okay, what would you expect right there? See if someone comes with an answer. What would you expect to see where the plates split apart? Plates are splitting apart. What's going to pop up in between? Good. Okay. Both of those. Okay. Lava and volcanoes. Now, if you want, okay, it does shift the currents, okay, but it wouldn't actually replace them, okay, because it's liquid rock that's coming up, not hot water, okay, and it's really deep in the ocean. That's an interesting point as well. Thanks, Hannah. Okay, so it's coming up. Okay, so we've got lava being built up. Okay, if you look, I always do this with my class. Two things. Okay, two things to do with my class at this point. First of all, we look at pictures of underwater volcanoes. Okay, so Google that, underwater volcanoes. That's what's happening here. We've got this underwater volcano. Okay, so we got this lava being pushed up. Now, pushed up, lava coming out. These plates are splitting apart. We've got this crack right through the middle of the Atlantic. Another thing you can look up is the Mid-Atlantic Ridge. Okay, I'll write that down over here. Mid-Atlantic Ridge. And that's what you'll see. If you look at a view of the Earth, you'll see this crack going right down the middle of the Atlantic. That's the Mid-Atlantic Ridge. That's where two plates are forced apart. You've got this crack right in the middle. Now, as Connor and, okay, if you look at the pictures, it's really cool. Okay, the water doesn't fall down. It's surrounded in water. So basically, it's, okay, the lava comes out. It cools really quickly. So it turns into a rock really quickly. Okay, so it doesn't stop it because it's really, really hot, but it just sort of blurs out. Okay, it's kind of cool, kind of gross looking video. Okay, so we've got this happening here. We've got this lava building up. And hey, it's come up above the water. What do we call a volcano that's above the water? Kind of a trick question. Maybe you can think of it. What do you call a volcano that rises above the water like this? So you have this piece of land in the middle of the ocean. What do we call that? One more second. It's called an island. So we have these islands that are being formed. Thank you. Awesome. Islands are formed by convection currents, which is pretty awesome to think about. So this island, okay, let's give it a name. Okay, let's call this island Iceland. That's why Iceland is there. Iceland is there because convection currents happen in the middle of the Atlantic, pushing two continents apart. The lava comes in between. We get Iceland. Okay, we get an Iceland. Okay, what do you know about Iceland? Well, it uses geothermal energy. Why does it use geothermal energy? Because it's sitting on a volcano. Okay, that's Iceland. There are also other islands in here. If I draw a little mini map, okay, of the Earth, okay? Here's Europe, okay? Here's Africa, here's South America, here's North America. All through here, you have your mid-Atlantic ridge. Iceland shows up here, the Azores show up there, okay? There's also islands off the coast of Spain. Those islands are all there because this is happening underneath, okay? North America and Europe are getting farther apart. They're being pushed apart, just like you can see South America and Africa getting pushed apart. Okay, this whole process is called plate tectonics, and you can use that in your paragraph at the end as well. So we have plate tectonics. We have plates on the surface of the Earth floating on the mantle, being pushed this way and that way because of convection currents that are happening in the Earth, okay, in the mantle, going up, going across. These two are being forced apart. Now, if these two are being forced apart, obviously at some point we've got to have, okay, two places, okay, so if we change this to North America and change this to Europe and then Russia, okay, Japan's over here, okay, we've got a plate going under Japan, okay, so these ones are being pushed together, okay. So if I were to draw the other convection currents, this is going up, okay, and it's, sorry, this is going up and it's pushing this way. So these two plates are coming together, okay. How do I draw that? These two plates are coming together, these two plates are coming apart, okay. So in Japan, okay, we've got these two plates, okay, coming together. So they're being forced together, okay? These ones are being forced apart. So Japan is happening because of convection currents. One more, okay? One more. And it has to do with what we just talked about. So what I'm going to get you to do, I'm going to get you to picture a plate, okay? A tectonic plate, oceanic plate under the ocean, okay? We have a convection current that's going, actually, let me put the convection current over here. That's going up and it's pushing this continent this way. Okay, this plate this way. Now, we've got a crack in this plate. Okay, let's put it over here. Okay, we've got a crack in this plate. Okay, so in this plate, you've got the ability for this hot stuff to come through. Okay, so it comes through, it comes through, it comes through, it comes through. It forms an island. Okay, now over time, this island shifts over. This plate shifts over because the convection current is pushing it this way. So the convection current is pushing it this way. This plate shifts. This island shifts over here. And then you've got the crack over another place. So we've got another island forming. Okay? This whole plate shifts over. We've got an old, let's do this, oldest, older, okay? And we've got an old one, okay? So we've got this chain of islands being formed, a chain of islands being formed, okay? And it goes this way, okay? Oldest islands are over here. The youngest islands are over here because they're right over the crack. The convection current is pushing it over. This is the Hawaiian Islands. The Hawaiian Islands are caused from this process. There's a convection current pushing the plate over. We've got crack here, islands, islands, islands. That's why Hawaii is a chain of islands. Now, what Disney short, and this is where I stop and we try to find it because it usually takes forever. What Disney short shows this process, shows convection. And then the next time you watch it, you can say, hey, science. What Disney short shows this process, an island getting formed and an old island dying. Yep. Exactly. I love a you. Okay. I love a you. Hawaiian song. Okay. He plays the ukulele. Hawaiian song about islands that are getting old and new. So this is the girl island. Okay, this is the boy island. Okay, boy island is moving away. So it's getting older, it's getting eroded, it's falling apart. The girl island is being formed. She pops up. Okay, so Disney knows about convection currents. I don't know if that's true or not, but Disney might know about convection currents. Okay, this is how Hawaiian islands were formed. So you can use any of these examples on the last question. You can talk about wind, onshore, offshore breezes, global winds, ocean currents, mid-Atlantic ridge, plate tectonics. I wouldn't talk about the Hawaiian Islands because it doesn't show the full convection current, okay? But it is caused by a convection current. I'm also going to put in, I'm going to put in the Eureka video. The Eureka video is going to talk about two things, okay? First of all, it's going to talk about how you heat your house, okay? By the way, okay, this right here, okay, is producing a lot of heat. If you put your hand above it, okay, it's hot because heat rises, okay? By the way, you may see this at provincial campgrounds. I always notice the trees right above the fire are really dead, okay, because the heat rises and kills those leaves. Now, over here, Hannah, you are welcome to use your own example. Okay, I'd love to know about it so I can talk about it with the class. So if you type it in, I can help you and help the class understand. This, we have a hot water heater. Okay, so the hot water, and this is what the Eureka video is going to talk about. The hot water, okay, gets hot, becomes less dense, and rises. Well, it's going to rise through these pipes. Okay, it's going to rise. Oh, sorry, these pipes at the back. It's going to rise through these pipes. Okay, it's going up through these pipes. Okay, and it's going to move through here. Okay, so the hot air rises, hot air rises, hot air rises, hot air rises. Okay, and sorry, in this case, hot liquid rises, hot water rises, and it goes here. Okay, this is a hot water heater. So it goes up and through here. Okay, and it heats up, and then it goes back down to cool. Okay, so those are heating your home. If you have air, it does the same thing. Okay, if you have hot air, it does the same thing, right? The reason why your house gets hot is because it rises. Yeah, Hannah, how are you going to show that it goes all the way back down? I'm not sure. Okay, that's a good example. That's a great example. Okay, we all know the heat rises from a campfire. Think about how you could show that as a current. Well, you could just talk about the ashes coming back down, right? The ashes don't rise forever. The ashes come back down. All right, fantastic. Fill out the sheet. I am going to pop in that Eureka video. I'm sorry I didn't do it earlier. Okay, you need to make a copy of that sheet and then fill it out, submit it, and we're good. Thank you so much for joining me. Okay, appreciate it, and I will see you later.